My name is Ian Dunn, and I'm ESR number 6 in the Smart ETN project. In this short video, I intend to give you a rough introduction to my project and explain why it is important. My research concerns the dynamics of rail and road bridges. My research project specifically considers an analytical method to model the response of a bridge to any number of forcing actions. The aim of this study is to produce an efficient mathematical model which can be used to develop and better understand novel damping devices. For that reason, I'm going to move from my office to the Experimental Dynamics Laboratory here at the University of Palermo, where I'm based. Here behind me is a simple, small-scale model of a bridge, which has been constructed in our laboratory to validate our analytical model. It features an acceleration ramp and a single span beam, which is traversed by the moving load. This test setup is based on experimental models which are present in literature, and as expected from the results of previous studies, in its current configuration it shows a very good agreement with existing mathematical models. However, at this point in the experimental testing, there is no novelty. It is a single span beam subjected to a moving load, and as previously stated, this problem is present in and has been validated in literature. We therefore intend to add intraspan damping devices and compare the experimentally obtained results to our new analytical model and to existing mathematical models. This is novel. Damping devices are widely used in existing infrastructure. Their purpose is the reduction of the maximum deflection of the structure to which they are fitted and the mitigation of the dynamic forces acting upon that structure. You may be wondering why this is important. The short answer is that dynamic forces cause significantly greater loading than static forces and resultantly can cause serious structural damage if left unchecked. In the case of rail and road bridges, there are a number of dynamic forces incident on the structure. One of the most prominent forcing actions is caused by the vehicles crossing the bridge. This is why you may have noticed that many bridges that you have driven across will have a different speed limit from the road network leading to and from them. Higher speeds increase the dynamic forces, and therefore the response of a bridge to a dynamic force must be very well understood, particularly now, when high-speed rail projects are receiving significant investment and public interest. Using a laser vibrometer, we're able to extract the mode shapes and modal frequencies of this beam. This gives us an indication of the way that the beam is vibrating, and the natural frequencies allow the selection of the optimal tuning parameters for the tuned mass dampers, or TMDs for short. TMDs are damping devices consisting of three parts: a spring, a small mass, and a damping element, all of which fit together. TMDs are well understood and offer a tried and true method to mitigate the dynamic forces caused by moving loads, wind forces, or ground motion. Now, briefly before the end of this video, I would like to discuss the analytical method which has been developed and its advantages over other analytical methods and the importance of robust analytical modelling. To do this, I'm going to have to move again to somewhere where I can show the mathematical method. This, I'm afraid, is the tedious part, but hopefully you'll find it moderately interesting. So a bridge can be modelled as an Euler-Bernoulli beam. This is an elastic beam model, an analytical model I should say, which has existed since the 1700s. But it didn't really become prominent until the advent of computers, which allows this very complicated analysis to be conducted quickly, as opposed to in the very time-consuming and inaccurate by-hand method. The classical analytical method provides very accurate results, which correlate highly with those obtained by experimental analysis. But there's a problem. It's not very efficient, and as the model becomes more complex, this inefficiency grows. For a single-span bridge, such as the model that we looked at in the lab, the classical method is not particularly complex, and it can be solved by most modern computers in a matter of seconds. With the addition of intraspan dampers or intraspan supports, however, the complexity of this model will grow and grow as we have to consider each span individually. The equations contained here in this presentation should help me illustrate this. So, for a single span beam, we need only one equation of motion. in which there will be 4 unknown constants and 4 boundary conditions. To find the unknown constants, we enforce the boundary conditions which are present at the supports and are thus always known, provided we know what kind of supports there are, and we will always find a solution. For multiple spans, one equation of motion is required for each span. A 4-span beam, such as what's shown here, with 3 TMDs, means that there will be 4 boundary conditions for each span and 4 unknown constants for each span, giving us 16 in total. All of these are coupled, and the amount of computational time required to solve this is increased dramatically, from a few seconds to 10 to 20 minutes. Again, these numbers shouldn't be taken as written because it's on my computer. With more advanced computers, 10 to 20 minutes could be vastly reduced. But consider the amount of pillars and supports that you see on an average motorway bridge or on-ramp to a motorway. And imagine the complexity involved to find the response for a relatively simple problem. That's where a more efficient method, namely our method, plays a pivotal role. The proposed method models these supports and damping devices as point forces acting on the attachment points. And as such, there are only ever 4 boundary conditions, and the solution is found, as in the first case, rather quickly. This is done through this term here, Pj of t, which, as I mentioned, models, in our case, a tuned mass damper as a point force. For more information on the topic, I'd be happy to answer any questions that you send to me. And there are also a number of papers that have been published, which you're surely able to find. So thank you for your time, and at the risk of sounding overly Americanized, have a wonderful day. Thank you.